I welcome all of you on platform of YourPedia Education, and this one is the third lecture of 50 most important topics in physics which you can expect in your upcoming exam, that is ATC exam, Airport Authority of India exam. And first two topics were related to electric flux and Gaussian equation, Gauss law of electric flux. And this third lecture is also related to that. In fact, this one is the extension of the second, and it tells you about the application of Gauss law to find out electric field at some particular point. So let me tell you what we have done so far. We discussed about electric flux. We talked about what do we mean by electric flux, and electric flux we wrote with this particular symbol, which is nothing but E dot dA, that is integration of this electric field and the dot product of area and over the surface. If we calculate, we get the electric flux. That means electric field lines coming from particular surface area, that is called electric flux. Then we discussed about Gauss law, and Gauss law was also derived using this particular concept only, and that says that electric flux is equal to Q by epsilon naught, where Q is the charge enclosed by particular surface. We called it Gaussian surface. If I give you a diagram of a cubic shaped body, let us say there is a charge Q inside this cube, then what is the total electric flux which will come from this particular surface outside? That will be Q, total charge enclosed, divided by epsilon naught. That is a Gauss law. Now this third lecture is the application of Gaussian law, application of this particular law. And you know, this particular entire thing will be used to find out electric field, to find out the electric field because of, due to either charge or charge distribution or charge distribution. So this particular lecture is related to that. Can we find out the electric field because of some particular charge? We know one formula which we have done already, that if there is a charge Q, a point charge, and at r distance, suppose I want to find out the electric field, the formula is 1 by 4 pi epsilon naught Q by r square. Now this formula is for the point charge small q. Electric field because of this point charge at distance r is calculated like this. Now suppose we do not have point charge, we want to find out the electric field because of the charge which is distributed or couple of charges. How to find out electric field because of this situation? Now what we will do, we will make a Gaussian surface enclosing the charge. So the steps what we will be taking is, make the Gaussian surface, make Gaussian surface enclosing the charge, enclosing this charge or the charge distribution. The moment we have made the Gaussian surface, after that we will be using Gaussian law, and the moment we use Gaussian law, after that we can find out the electric field. Now there are some very important cases which we are going to discuss in today's lecture. One case is, there is a infinitely long wire having charge distribution, very long wire having charge distribution, and I want to find out what is electric field at some distance r because of this very long very long wire carrying the charge on it. Second case can be, I give you a surface, again very large size surface having the charge distribution. Now think of a sheet, something like the board this particular board. Now assume it to be very, very large, sheet of infinitely large size. That means uska ye dimension is very large, this dimension is also very large, and this dimension is also very large. So that means the size is very, very large. Now can you find out again the electric field because of this distributed charge on this sheet? This is the basically wire, this one is sheet. You know the difference between the two. This is two-dimensional entity, this is one-dimensional entity. This is 1D only length, this is 2D, it is a plane, and then we can think of three-dimensional things also. What is three-dimensional things? I may give you a particular cylinder having the charge on its surface. So I give you a cylinder, again it can be of infinite size on particular side, length or something, and we want to find out what will be the electric field at distance r from its center, what will be the electric field because of this charge on the cylinder. Or instead of cylinder, I can give you the spherical shaped body also. So whether can you find out the electric field at distance, let us say r, from the center of this spherical shaped body. This is the cylindrical shaped body, cylindrical body, spherical body, and you know these cylindrical and spherical bodies have charge densities, that is charge is distributed charge on their surface. In this also we will be talking about conducting and non-conducting. We will be talking about conducting and non-conducting or dielectric bodies. Conducting or non-conducting. Non-conductings are also called dielectric surfaces. The cylinder can be conducting if it is conducting, or conducting, non-conducting, it can be solid and hollow also. So we will be discussing all these cases, important cases: cylinder, sphere, wire, sheet. Only these four cases from where exam may he can ask you question. Using the Gauss law, find the electric field at particular position, and then he can ask you to draw the graph or something like that. So we have to do only these four cases. There is a wire with uniformly distributed charge over its length, very long wire. There is a sheet of uniformly distributed charge over its surface. There can be solid or hollow cylinder, solid or hollow sphere, conducting or non-conducting, having charge distribution on its surface, and you have to find out the electric field intensity because of this charge at particular distance from these surfaces. Now before we go forward, certain thing is very important to understand and remember, and that is charge densities. When we talk about charge densities, we will be talking about three kind of charge densities, like density, mass per unit volume. Charge density is also of three types, and we will be using these three terms. Charge density, this is charge per unit length, this is charge per unit length, this is called linear charge density. Let us say this has lambda linear charge density. Now suppose I want to find out the charge in particular length L, then I need to multiply delta with L and I get the charge over length L. Sigma is nothing but charge per unit area. This is called area charge density. This is the basically area charge density. So if I want to find out the charge in particular area, then I can multiply that area with sigma and I can get charge in that. In this case also sigma may be useful for us. And then comes volume charge density. This is charge per unit volume. So in this particular case I can make use of volume charge density. Rho is the volume charge density. So if I know the volume charge density as rho, I can calculate the basically charge over particular volume. So if the charge is distributed, I should know what is the distribution of the charge. That is very important. If the charge is distributed, I should know how it is distributed, lengthwise, area wise, or across the volume. Depending upon that, we have three kind of charge densities: linear charge density, surface charge density, volume charge density, and these are the typical cases. So with this lecture, third lecture, you will be completing a very important topic for physics, and that topic is related to electric flux, Gauss law, and the application of Gauss law to find out the electric field. So the ultimate purpose of Gauss law is to find out the electric field, and then a couple of questions can be asked from there. Now we go for one by one case, and I give you the first case. Here it is the first case. Now I give you infinitely long wire with the linear charge density as lambda. Infinitely long wire with uniformly charged, uniform linear charge density. So lambda is linear charge density, linear charge density, and this is the uniform charge distribution. We are assuming the charge distribution is uniform charge distribution. Now whenever you want to analyze some particular thing, first thing you should do is you should try to find some kind of Gaussian surface. So let's make some Gaussian surface here. I make this as a Gaussian surface enclosing this particular charge. Let us take the length of this as L, and let us take the radius as R. And remember, you should be clear about what Gaussian surface you have to take. For linear, for a line, for a wire with uniform charge density, Gaussian surface enclosing that wire symmetric around the wire is cylinder only. That is easy for us to analyze. So it has to be symmetrically located, that means wire at the center. Now how many areas do you see here? I see three kinds of area: top surface, bottom surface, and then curved surface. These are the three surfaces which I see. Now what is the Gauss law? If you see, the Gauss law says electric flux is nothing but E dot dA is the electric flux, which further is equal to total charge enclosed inside charge Q inside over epsilon naught. Now E and dA, electric field and area vector, the angle between these two is theta. Now suppose I talk about this surface. You see the area vector is this side, and if you see the charge, electric field vector will be this. Angle between the two is 90 degree. Hence if you see this E dot dA, what do you get from here is E into, for first surface, this particular thing, if I want to find out flux, that is for first surface, top surface, bottom surface, and then third. Let me give the name. This is 1, this is top surface 2, and 3 is the curved surface. Now if you see the first and second may, the area vector and electric field vector are perpendicular to one another, and hence phi 1, phi 2 will be equal to 0. These two will be equal to 0 because area vector and electric field vector are at 90 degree to one another, and only thing flux is now because of this curved surface of cylinder. Now let us assume there is an elemental area here dA and electric field vector E and elemental area vector dA are in the same direction. So what is phi now? It is equal to E into dA integration, because there will be so many such area vectors. So area vectors will be small elemental areas I can take at numerous positions. E everywhere is same, and that means if I take the distance at R distance, if I take, then electric field is same, so I can take E outside. This becomes E into dA. That is what I get it. Now for this Gaussian surface, can you tell me how much is the charge inside it? So Q inside is equal to linear charge density into this length, that is L. If I take length L, the charge inside is lambda into L. Now if I put that thing in this equation, I get E into dA is equal to lambda L over epsilon naught. And what is dA? dA is nothing but now this entire curvilinear area, which is nothing but 2 pi r into L. So 2 pi r into L is the curved area, is equal to lambda L over epsilon naught. This helps us to calculate the value of electric field because of this wire at any distance r is equal to lambda over 2 pi epsilon naught into r. This is very important formula. Now in the exam directly this formula can be asked. What is the electric field because of the wire? Now what is the electric field if I give you a wire with uniform charge density lambda? Suppose I give you a wire with uniform charge density lambda and this wire is infinitely long wire, then at distance r what will be the electric field? That is 1 by 2 pi epsilon naught. In fact it is lambda over 2 pi epsilon naught into r. This formula you need to remember, and if somebody asks us to draw the graph between radius and E, this is how the graph will be formed. So electric field and radius graph is to be drawn like this. I hope this particular concept is clear to us. So what we did is we took a long wire having uniform charge density of lambda, linear charge density, and then I made Gaussian surface around it. The moment I made Gaussian surface around it, I enclosed particular length of the wire, and in that I enclosed particular charge in that. So that charge which was enclosed is lambda into length, lambda into L. So I can now basically know what is the charge inside. Lambda into L over epsilon naught is equal to E dot dA. So all I am to do is I am to calculate E dot dA for this Gaussian surface. This is how it is to be done. Okay, that is first case we have done. Now we go to second case, and the second case I am giving you is now about electric field due to plane sheet. So now let me make this diagram for you. Again I am giving you now a plane sheet of infinite size having uniformly distributed charge, and in this case because we are talking about area, so we will be having surface charge density sigma. So sigma is charge per unit area, charge per unit area. So now we have got sheet, charged sheet. This is charged sheet of infinite size. Now can you find out the electric field, let us say at particular distance r? Suppose I want to find out now what will be the electric field at distance r from this sheet, and now you understand whether I calculate this side or I calculate this side, it is more or less same. So what is the electric field at distance r from this particular sheet? The first thing we have to do is we have to make a Gaussian surface. We are to make the Gaussian surface. So again let me make this Gaussian surface here, and I make this as Gaussian surface. It is a cylindrical surface. Now I have made basically a cylindrical surface enclosing some particular charge here. So I have taken this cylindrical surface as Gaussian surface and enclosing particular area of this sheet, and then after that we can cover entire sheet. The Gaussian surface here is cylindrical shape. Now this cylindrical shape has three areas. One is this area, cross section area, and curvilinear area. Now if you see, electric field and area are in the same direction. What about this? Electric field and area vector are in the same direction. Now see this carefully. Area vector is perpendicular to the surface of area. So area vector is this side, and because the positive charge, electric field is also this side. Similarly, area vector is this side, and because this is a positive charge, electric field is also this side. So for this Gaussian cylindrical surface, electric field and area vector are in the same direction here. But for the curved surface, electric field and area vector are perpendicular. So there will not be any electric flux through curvilinear part of this cylinder. No, basically you will get no electric flux through this curvilinear part. That is what you have to understand. Now let's apply the formula of Gaussian law now. So what is the electric flux? Electric flux is E dot dA integration is equal to charge inside over epsilon naught. Okay. Now can you tell me what is the charge inside this particular cylinder? Now if I give you again the diagram of the cylinder, it is like this. Let's make the diagram of the cylinder. This is the Gaussian surface I have taken. I am making little larger diagram. This is the Gaussian surface, and this Gaussian surface contains this particular sheet which we have provided. Let us say this is the sheet provided, and now this particular Gaussian surface basically is cutting this part of the sheet. This is the area. Let us say this is the area A, this area A, this area A. So this A contains the charge. So what is inside charge? Inside charge is area into the surface charge density. So this is the charge Q in which actually this cylinder is having from the plate. This is a very infinitely large plate, but this part is cut by the cylinder. So that is the charge we have. So that is sigma into A. Now what is E into dA? EA plus EA. So we got this E into dA as 2 times E into A. Why 2 times? Because this is electric flux, this is also electric flux, something which is coming out. So what we get from here is now this Q inside is sigma into A over epsilon naught. So what we get is 2EA is equal to sigma A by epsilon naught. So what we get, electric field is sigma A gets cancelled out, sigma by 2 epsilon. Again very important formula. So if I give you infinitely large size sheet, what will the electric flux, electric field at particular position is to be calculated like this. And now you see this carefully, it is independent of, this one is independent of the radius, it does not depend upon the radius. So suppose he asks you to draw the electric field now, the graph between electric field and radius, you are getting constant value, that is sigma by 2 epsilon naught. This is something which is very important finding. Infinitely large size sheet, what will be the electric field at some distance from it? Sigma by 2 epsilon naught. Sigma you should know, and epsilon naught is a permeability, you already are aware about this. This is how it is to be calculated. So let me give you a question here, very small question. I give you 2 sheets. This is one sheet and this is another sheet, let us say, and these 2 sheets are subjected to uniform charge distribution, but only thing is one is having positive charge, another is having negative charge. Let us say this is the sigma positive, this is negative sigma. There are 2 sheets of infinite size, very large size, and charge density is positive and negative. Okay, let me give you a point A, let me give you a point B, and let me give you a point C. What will be the total electric field at A? Now you understand that does not depend upon distance. Let us say this is sheet number 1, this is sheet number 2. Because of sheet 1, electric field on A will be in this particular direction, away from, because positive charge. Here the charge is negative. Because of negative sheet, the charge, the electric field acting at point A, because of this second sheet, will be also in this direction. Why? Because it is negative. This is positive, electric field is away from it. This is negative, electric field is towards it. Can you tell me, because of second sheet, what will be the electric field at B? And what about A? right? Now at C, electric field because of first will be this and because of second will be this. What is total electric field at C is 0. Why? Because electric field का formula अभी आपने निकाला Q by sigma by 2 epsilon naught, and this is independent of the distance. It is dependent only upon sigma. So one side sigma is positive, another negative. It will cancel out. EC is 0. Similarly, EB is also 0. What about E at A? E at A will be equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. It is in the same direction it is added. So sigma by epsilon naught. Sigma by epsilon naught. And this particular concept later on you will see, this concept is used in capacitors. So बाद में आप ये देखेंगे ये concept capacitors में use होता है. Parallel plate capacitors वो एक important topic है. Parallel plate capacitors को हम करेंगे. We will do that because that is also one of the most important topic for your airport authority exam, like Gaussian law, electric flux. तो ये भी आपका कैपेसिटर का बहुत इंपॉर्टेंट टॉपिक है. वी विल डू दैट. सो कैपेसिटर में ये कंसेप्ट आपका यूज होता है. अभी सोचो अगर इफ आई गिव यू 2 प्लेट्स बोथ पॉजिटिव, 2 प्लेट्स बोथ पॉजिटिव, तो ये कितना हो जाएगा 2E, ये कितना हो जाएगा 2E और ये कितना हो जाएगा 0. अंडरस्टूड दैट? सो अकॉर्डिंगली यू नीड टू कैलकुलेट द वैल्यूज. सो फार आई थिंक यू हैव अंडरस्टूड. वी आर डूइंग द एप्लीकेशंस ऑफ गॉसियन फॉर्मूला, गॉसियन लॉ, उसका हम एप्लीकेशन कर रहे हैं. And we have taken, we are calculating the electric field because of some particular charge. In fact, uniformly distributed charge on a particular wire of infinite length or a sheet of infinite size. And then there are 2 more things which are now left. One is the cylinder and another is sphere. Now electric field because of charged cylinder, let's talk about that. Electric field due to charged cylinder. Now let me tell you, we will be categorizing cylinders in 2 categories. There are 2 broad categories in which we will be dividing it. These are the 2 broad categories. One is solid conducting cylinder. Second, hollow conducting cylinders. Solid conducting cylinders, hollow conducting cylinders, and hollow non-conducting. This is one category. Second is solid non-conducting cylinders. Now what is the difference between the two? How the analysis of the two is different? I tell you, if there is a solid cylinder but conducting, entire charge is on the surface. Listen this carefully. If there is a solid cylinder, let me give you the diagram again. This is the top view actually is being made, so let me give you the diagram. Let us say I give you this cylinder. It's a solid cylinder लेकिन conducting है, solid cylinder but conducting, so entire charge goes on its surface. This is solid, no charge inside, no charge. So there is no charge inside the solid cylinder because entire charge goes on the surface. Suppose I give you this cylinder now, which is solid but non-conducting, then the charge is uniformly distributed over its entire body. Charge is uniformly distributed over its entire body, and that is the reason the analysis is little different. So I can divide even cylinder and sphere also. There are 2 broad categories of cylinders and spheres depending upon the charge distribution. One is all these 3 are one category and this is another category. What is the difference? If the cylinder is conducting, solid, hollow conducting or hollow non-conducting, then entire charge will be on the surface, right? And we need to calculate the surface charge density. In this particular case, he will be giving you surface charge density sigma. But if it is solid non-conducting, then the charge is uniformly distributed over its entire body. In that case, he will give you the volume charge density, that is, he will give you the value of rho instead of sigma. He will be giving you the value of rho. And how to calculate the charge? Then that is a rho into volume within which the charge is distributed. That is true for cylinder also and then sphere also. It is same. We will be doing the same thing there. Now let us first try to analyze the solid conducting cylinder, and because this category, that is something which we are making this entire category. Now let us say there is a cylinder. Let me give you the diagram of this cylinder now. Let us say there is a cylinder, but it is of infinite size. That means one of the dimension is very long, length is very long, infinitely long cylinder, something like this. And let us say the radius of this is r, right? And because it is conducting, so what we understand is entire surface, entire charge is distributed on its surface. And let us say this is the central axis of this cylinder. It is infinitely long. I hope the diagram is clear. There is a cylinder of radius capital R, length is infinitely long, and entire charge is distributed sigma over its surface. And what is the question? What we want to do? We want to find out what will be the electric field at some distance, let us say r. What will be the electric field at some distance r because of this cylinder? That is the question. That is the derivation we are going to find out. हमें एक Gaussian surface लेना पड़ेगा, and again the Gaussian surface which we take can be cylindrical surface only. So let me give you a cylindrical surface only, Gaussian surface, this one. Let's take a cylindrical surface again which has a length of L. Let us say this length is L and the radius is R. Maybe you can visualize this as cylinder. Now I encircled the conductor within the Gaussian surface. मैंने Gaussian surface के अंदर इस cylinder को ले लिया. Only difference is Gaussian surface has a radius small r. I want to find out electric field here, and the length is L. Now electric field and area vector, this surface, area vector is this, electric field is this, area vector is this, electric field is this. So there is no electric flux from the top surface and bottom surface. There is electric flux only in the curvilinear part. What is the formula do we have? The formula we have is E, let's create some space here, E dot phi is equal to E dot dA integration is equal to Q in over epsilon naught. That is the formula for this particular flux, electric flux. E dot dA is Q by epsilon naught. Now, what is the charge inside this Gaussian surface? What is the charge inside the Gaussian surface? You know, charge inside Gaussian surface is, if you tell me the surface area, what is this surface area? This is sigma into 2 pi r into L. R is capital R into L. This is the surface area of that cylinder within length L, and entire charge is distributed over this surface, curvilinear surface. So we have this particular value. And now this surface area, this EA0, this EA0, what is left is E into 2 pi. Now what is the area? 2 pi r into L is equal to sigma into 2 pi r into L. Certain things gets cancelled out. Sigma over r, L gets cancelled out. Just check it out whether we get, yeah, and this is to be divided by epsilon naught. So sigma by epsilon naught, and this E is inversely proportional to r. Just check it out. The formula for this is coming out to be sigma by epsilon naught capital R over small r. Again this is a typical formula. Now you need to remember the formula. Copy पे लिखते जाओ. Formula आपको याद रखना है. How much value you are going to get? Sigma by epsilon naught and capital R over small r. अगर ग्राफ प्लॉट करोगे E and R में, so this is the graph which we are going to get it. So for this all the cases, this is the expression for this. Now we are left with this particular case. This is a case where charge is uniformly distributed over entire body. Charge is uniformly distributed over entire body. So now here we get the cylinder where charge is uniformly distributed because it is non-conducting, now non-conducting cylinder. So the charge is, we have got non-conducting cylinder, and in this case because it is non-conducting cylinder, he will give you now charge, volume charge density as rho. Volume charge density given will be rho. Now this has two expression further. I can derive now, I can analyze it in two ways. Number one, what will be, the electric field inside it. So the Gaussian surface I took is this. See this carefully. This radius is r, that is the cylinder which is given to us, and I take radius small r. Gaussian surface is taken inside it. There can be another case also, and let me make the diagram. This is the actual non-conducting cylinder which is given to us, and the Gaussian surface I can take is, now I can take Gaussian surface of larger size also, something like what we have done earlier, right? So I can take Gaussian surface of radius r, and जो मेरे पास दे रखा है सिलेंडर उसका रेडियस है कैपिटल R. You see this carefully what I have done. This has further two cases. One, if I want to find out electric field inside it. Another, I want to find out electric field outside it. So Gaussian surface का radius I will say R is less than R. Second, R is greater than R. These are two cases which we get it. And what is our typical formula? Electric flux, that is nothing but E dot dA integration inside charge over epsilon naught. Inside charge over epsilon naught. That is the formula which we have got. Now, what is inside charge? In this particular case, what is inside charge? Q inside is nothing but rho. Can you tell me what is the volume of this cylinder? Okay, volume of this cylinder is pi r square. This is radius r into L. Pi r square into L is the volume of this cylinder, and hence this becomes the inside charge. And can you tell me now, where will you get the electric field? Now, because in this case the electric field is in this direction, area is in this direction, so what we are going to get is the electric field on this Gaussian surface will be only because of the curvilinear part, not other part but curvilinear part. So what we are going to get here is the electric field, actually we are going to get is E into 2 pi r. So E dot dA is nothing but E into, what is the area, 2 pi r into L. So I am assuming it to be of dimension L. I am taking it to be dimension L. So I am finding that if I want to find out what is the electric field because of this Gaussian surface, मैंने अभी Gaussian surface मेरे को अंदर इलेक्ट्रिक फील्ड फाइंड आउट करना है, तो मैंने अंदर देखा कितना चार्ज पड़ा हुआ है, इतना चार्ज पड़ा है इसके अंदर. Gaussian surface ये है मेरा, तो इसके अंदर कितना चार्ज पड़ा हुआ है, दिस इज द चार्ज इनसाइड इट. ओके, इफ दिस इज द चार्ज, इलेक्ट्रिक फील्ड मेरे को निकालनी है बिकॉज ऑफ दिस चार्ज. सो नाउ यू नो area vector and electric field, they are perpendicular on this surface and this surface, only curvilinear surface का एरिया आएगा, 2 pi r into L part will come. So if I equate these two, what I get is E into 2 pi r into L is equal to rho pi r square L over epsilon naught. अब कुछ टर्म्स कैंसिल हो जाएंगी, L will get cancel out, pi r will get cancel out, तो rho r over 2 epsilon naught, rho r over 2 epsilon naught. And you observe one thing here carefully, that E is proportional to R. That is very very important. So अगर non conducting cylinder है, and if you want to find out, the cylinder is non conducting, and if you want to find out the electric field at some distance R, then electric field is proportional to R. That is different from earlier case. Electric field was coming inversely proportional to R. अभी क्या है, non conducting cylinder है, उसके अंदर चार्ज पड़ा हुआ है, and if you want to find out electric field inside that particular cylinder, this is how it changes. Inside वो इस तरीके से change होता है, right? Now what is the difference between this and this? E into 2 pi r L will remain same. Now what will the electric field at this point I want to find out? So E into 2 pi r into L, L is this length. So electric flux because of the curvilinear part, और जो अंदर आपका चार्ज डिस्ट्रीब्यूटेड है उसका इलेक्ट्रिक फील्ड एट एनी पर्टिकुलर पॉइंट इफ यू वांट टू फाइंड आउट. सो दिस इज E into 2 pi r L, and what is the now total, this charge is distributed up to R. So this particular place will come rho into pi r square into L over epsilon naught. So instead of pi small r square, in this case it was small r square. Now the charge is distributed over capital R because entire cylinder is now inside that. तो इसमें क्या formula बन जाएगा अभी? So what E value you are going to get in this particular case? Now certain things will get cancel out, L will get cancel out. So this comes out to be rho r square, pi gets cancel out, 2 epsilon naught into R. So this is the value of electric field, rho r square over 2 epsilon naught into R. So this is, if you see the value now, this is inversely proportional to R. तो अगर मेरे को इलेक्ट्रिक फील्ड का अभी डायग्राम अगर मेरे को प्लॉट करना है, इलेक्ट्रिक फील्ड, लेट्स से दिस इज रेडियस R, तो E is proportional to radius and then inversely proportional. E is proportional to R and then E is inversely proportional to R. So electric field non-conducting cylinder का इस तरीके से, this is how it varies, right? So this is not very important actually derivation. Non-conducting cylinder का बहुत important नहीं है. Wire is very important, sheet is very important, and first case of cylinder, conducting cylinder and all, they are very very important. So these expressions are important. Now the last thing which is left in this case is sphere. The last thing which is left is electric field due to sphere. This is the last topic, electric field due to charged sphere. And sphere को भी मैं दो पार्ट में I can divide. Spheres also I can divide in two categories. There are two categories of spheres. Number one, conducting, solid conducting, cylinder की तरह से. Number two, hollow conducting. Entire charge is on the surface. Hollow non-conducting. All this is one category, and solid non-conducting is another category. So what is so special about this? Charge is on the surface. The entire charge is on surface. So entire charge is located on the surface. And here, in this particular case, charge is distributed. So in this case, the charge is not on the surface. but charge is distributed in this particular spherical shaped body. That is how it is. Now let's go first. Here he will give you actually again the same, there is an analogy. In this case he will give you the surface charge density. Surface charge density will be provided to you, charge per unit area, and here volume charge density will be provided. Volume charge density will be provided. And remember, this case is more important compared to this case. This one is more important. Okay, so let me give you first case. मैंने एक spherical shaped body जिसमें entire charge is now conducting वाला part है ये, तो entire charge is on the surface and the radius of this is r and sigma is surface charge density. So what is the total charge now? Total charge is 4 pi r square into sigma. ये है हमारा conducting sphere. This is conducting spherical body. Conducting sphere हमारे पास ये आ गया. अभी मेरे को इलेक्ट्रिक फील्ड फाइंड आउट करना है. आई वॉन्ट टू फाइंड आउट इलेक्ट्रिक फील्ड. लेट अस से add some distance, which is add some distance, let us say, which is distance r. So how to do it is, one of the ways is एक Gaussian surface बना लो encircling this entire charge. So this is Gauss surface. Yeah, Gaussian surface in which the radius small r I have taken, and you see r is greater than capital R. So I have taken, in this case is very important case. Mark this important because ये मैं आपको इसका interpretation बताऊंगा why this case is important. So I have taken r more than this. Now what is the formula? Electric flux, let me write it with different color. So electric flux is E dot dA is equal to inside charge over epsilon naught. So let's take here elemental area dA and electric field E. So electric field everywhere is same. This is nothing but sigma into 4 pi r square over epsilon naught. I hope now you are understanding how it is coming up all. अंदर कितना सारा चार्ज है, that is surface charge density into अंदर वाला surface area 4 pi r square. Now what is this area, entire surface area? This is 4 pi r square is equal to sigma into 4 pi r square over epsilon naught. तो मेरे पास E कितना आ जाएगा, sigma r square over epsilon naught r square, and if you see E is inversely proportional to r square. That is how you should know this is entire thing. Right? And also observe one thing, अगर मैं इस expression को दोबारा देखूं, then what I can write, E into 4 pi r square is equal to inside charge over epsilon naught. See this formula carefully. E is 1 by 4 pi epsilon naught q over r square. ये formula देखा है क्या आपने कभी? This is a very standard formula. This formula is very standard formula. We are getting the same expression for this. Qi is sigma into 4 pi r square. That is a separate case. But suppose I give you entire charge Qi as a point charge. I give you entire charge as a point charge inside. Then what will be the electric field at this point r? Will be 1 by 4 pi epsilon naught q by r square. That means whether the entire charge Qi is point charge or this is the distributed charge, for us we are going to get the same formula. इसको ध्यान से सुनो दोबारा, ये सबसे important interpretation है. Spherical charged body, if there is a spherical charged body and I want to find out electric field because of that spherical charged body at some distance r, उसके beyond बाहर, I want to find out the electric field because of spherically charged body outside that body, then assume the entire charge on this body as a point charge located at one particular position at the center of that and calculate the electric field. द सेम फॉर्मूला विल कम। तो ये जो फॉर्मूला आपके पास आया, इसको इस तरीके से याद रखना है। इसको फॉर्मूला को ऐसे याद नहीं रखना, आपने उस तरीके से याद रखना है कि सारा जितना चार्ज है स्फेरिकल बॉडी पे, टोटल चार्ज कितना है क्यू आई, उसको उस स्फेरिकल बॉडी के सेंटर पे रख दो, एंड आर डिस्टेंस के ऊपर इलेक्ट्रिक फील्ड कितना हो जाएगा 1/4πε0 QI/r²। एंड QI को तो तुम सब्स्टिट्यूट कर लेना, दैट इज सिग्मा अगर दे रखा है यू कैन कैलकुलेट QI ऑल्सो। So that is the expression for this particular thing, right? So that simply means अगर मैं तुम्हें एक चार्ज बॉडी दे दूं, let's say I gave you a charged body, spherically charged body on which the total charge is Q, and I want you to tell me what will be the electric field at distance r. We will say 1/4πε0 Q over r square. Okay, what if I give you entire charge Q and then I ask you to calculate electric field at distance E? Because of this, that will also be 1/4πε0 Q by, both the formulas are same. So whether this entire charge is a point charge, whether it is a point charge or it is a distributed charge, or it is a distributed charge, as a spherical shell or spherical conducting body, you are going to get the same formula. That is something which is very, very important. And now last formula is spherical non-conducting body. This is the last case, not very important case like cylinder. Spherical non-conducting body. So electric field due to spherically non-conducting body. So in this case we now need to get volume charge density as rho. Okay, so इसमें भी दो केस आएगा. Let us say there is a spherical shaped body, radius r, and charge is uniformly distributed. So let me make little bigger diagram. I am giving you this. This is the spherical shaped body in which charge is uniformly distributed over its entire, and this is spherical non-conducting solid spherical body है ये, solid spherical non-conducting body, right? So this is the having radius r. This is also having radius r, and this charge is uniformly distributed over here. Right? So charge is uniformly distributed like this. Now what will be the electric field at distance outside this? What will be the electric field at distance r, and another is r is less than this? What is the electric field at this point? So r is more than r is less than r. There are two cases. I want to find out electric field at this point outside this body. I want to find out electric field inside this. So there are two cases. Formula we know is this: flux phi is E dot dA is equal to Q in over epsilon naught. What is Q in? Rho into 4/3 pi r cube. There is a inside charge is this. What is the volume of this? 4/3 pi capital R cube, and rho is the volume charge density. So total charge is this. Okay, and suppose I want to find out now what is the surface area here. Let us say this is dA. This is the surface area dA. So the moment I take surface area of this particular body, and the surface area of this body, if I take E into dA, E सब जगह से कॉमन आ जाएगा, this is dA, तो E into 4 pi r square, is equal to rho 4 by 3 pi r cube. If this is the entire charge q, I can take it as E as 1 by 4 pi, and this, yes, divided by epsilon naught q in by r square. Same formula which we have got in the previous case. Entire, charge, if I take, I can take entire charge as qi, या तो तुम qi को ही छोड़ दो, this entire charge on this is qi. What will the electric field here? E 1 by 4 pi epsilon naught, total charge q r square. So if you are calculating it outside, this case and this case is same, whether the charge is on this or charge is uniformly distributed, case is same. So ये आपका same case बनेगा, this one. But what about that? What about that case? Now in this particular case, E into 4 pi r square. Now what is the charge inside now? We will not take this entire charge, we will take now charge जो अंदर है यहाँ. Q in will be this, तो rho 4 by 3 pi r cube over epsilon naught. You see the difference? Here I am to take only this charge, not entire charge, because I am finding electric field inside it now. So कितना बन जाएगा? Certain things will get cancelled out. E will be equal to rho r over 3 epsilon naught. Rho r over 3 epsilon naught. So if you see, E is proportional to r, and if you see in this case, E is inversely proportional to 1 by r square. So as you go away from it, E is inversely proportional to this particular value, right? One important thing I want to discuss with you is this. अभी आपने इसको outside लिया. Can you tell me, if I give you a charged body, let us say charge conducting hollow body, and I want to find out electric field inside it. Suppose I want to find out electric field inside at this point. This one is our hollow conducting non-conducting body. If I give you hollow conducting non-conducting body, what will be E at R, that is inside that surface, will be 0. Why? Because there is no charge, so electric field will be 0. Now that brings us to an end of this lecture, which is very important lecture. मैं दोबारा से वापस चलता हूँ and try to make some sense of what we did. And this is, let me tell you, this is my third lecture on a very important topic, highly probable topic for Airport Authority of India. We are going ahead with 50 most important topics for Airport Authority of India exam. The first lecture was electric flux, that is defined as electric field lines crossing through particular surface area, that is electric flux. E dot dA, E is electric field. That is how we discussed about this. If there is a charge at distance r, what is electric field? We know this is the formula. Then we discussed Gauss law. If there is a charge enclosed in surface, what will be total flux? That is equal to Q by epsilon naught. And this does not depend upon shape, size of the closed surface. That is called Gaussian surface. So this particular thing is called Gaussian surface. This is called Gaussian surface. So you need to create a Gaussian surface, put the charge inside it, charge as a point charge or distributed charge. This Q can be point charge, it can be distributed charge. You need to think of Gaussian law, and then using that formula which you have found, using these two, you have to find out electric field at some particular point. That is this third lecture. First lecture was this, second lecture was this, third lecture is this. Then I told you that in this particular lecture we are going to find out electric field at a distance r from a wire which is infinitely long wire having linear charge density lambda, a sheet which is infinitely large sheet having surface charge density sigma, and what is the electric field at distance E on this side or that side. Then a cylinder with the surface charge density or volumetric charge density. Cylinder is there, infinitely long. So what is electric field? E outside it, inside it, and then sphere also. But in cylinder and sphere, we made two more classifications in cylinder and spheres, and these two classifications are, they can be solid, they can be hollow, they can be conducting, they can be non-conducting. So we divided this into these categories and then we kept on finding the formulas. तो सबसे पहले मैं एक वायर लिया और ये फॉर्मूला इंपॉर्टेंट है अपनी कॉपी पे. डेरिवेशन में नॉट बी इंपॉर्टेंट फॉर यू, दैट इफ आई गिव यू अ वायर ऑफ लैम्डा, then at r distance what will be the electric field. Abhi make the preparation very simple. Take a copy and on that copy make only one page of these formulas and they will be very very helpful for your exam. Only this formula you have to write. Derivation nahi karni hai, wo understanding hai. Ye formula likhna hai, that's it. And then if you know this formula, this everything is known. Only one formula. Next, sheet. Sheet में भी तुम्हें कुछ नहीं करना है. This only one formula. Sigma by 2 epsilon naught. And to understand, it does not depend upon distance. Then उसका कुछ application. अगर ऐसा कोई question आ गया, sigma by 2 epsilon naught, sigma by 2 epsilon naught, sigma can be positive, negative. तो ये आपका capacitor में use होता है concept. Then we came to cylinder and sphere. Cylinder में this is one category, this is the second category. Not important category. This is very very important category. So if this is the case, which we have done this, then what will be the electric field inside? That is 0. Inside is 0 because there is no charge inside. What is outside? The electric field outside formula is sigma r by epsilon naught r, inversely proportional to r. Formula बस ये लिखना है. Copy के ऊपर only this is the formula you have to write. Then we go for non-conducting. Not very important, non-conducting, but उसके भी दो categories हैं. It can be inside, it can be outside. Electric field inside, this is the formula. Electric field outside, this is the formula. Again copy पे लिखने हैं formula, that's it. Then we come to sphere. Again sphere can be divided into these two categories, and in the sphere, if the body is if I want to find out electric field at distance r outside, assume this entire charge as a point charge और formula तुम्हारे पास है. And how to calculate? Total charge is nothing but total surface area into surface charge density sigma. That is how you calculate. Very very simple case. And दूसरा case आ गया. This is only display of that. And also hollow sphere के अंदर और hollow cylinder के अंदर there is no electric field. And the last case is this, non-conducting. Non-conducting में you can take outside also. Non-conducting में outside is same as conducting outside. That is same. Non-conducting inside is this case. Looks like lecture, long lecture, but जब तुम copy पे उतारोगे, when you write the notes in copy, it will be 1 or 2 pages. That's it. And entire physics, let me tell you, for Airport Authority of India, entire physics will be only 10 to 15 pages. That's it. 10 to 15 pages, and you are done with your preparation of physics. Keep watching and keep understanding the concepts. This is simple thing. Physics is not difficult thing. Physics people are naturally we are inclined to understand physics. आसान topic होता है, करते जाएं and revise करते हैं. All the very best and keep going through all the lectures. Thank you.